So a solid sphere rolls off a spherical dome starting at the very top. Determine the angle theta at which the sphere flies off the dome. I know this is really bad lighting because, I don't know, I just have bad lighting. But there, hopefully you can see the drawing here. There's like a dome. A small sphere starts at the top, and then it's gonna roll off, and eventually it's gonna kind of roll off and then fly down, right? It's not gonna go down the whole way. Hopefully it makes sense that it's gonna fall off. And yeah, so what we got to do is determine the angle theta at which it flies off. This is like the thing that I got this from the AP Physics C packet at my school. They're silly, so they like to call it the bald man and Grape problem because they're just so silly. This is the Grape, I guess, and this is the bald man. Here's how you're gonna approach this problem, and it is a numerical value. Like, this isn't like a deriving equation. This is a numerical value. Even though you're not given really any variables. Here's how you're gonna approach this. So the thing you gotta understand, and then once you understand this, it's actually not too bad. When the instant it flies off, the normal force is 0, right? Because if you think about it, as it's flying off, there's no normal force, and then while it's on it, there is normal force. So there has to be an instant where the normal force is 0, and then it's gonna start, flying off. It's not in contact with the sphere anymore. That's why there's no normal force. So in that instant, for that one instant, it's still gonna be in circular motion, but then it's gonna gain speed and fall out of circular motion. So we can think of the net force on this block at that instant is going to equal mass times the centripetal acceleration. There's so usually it would be, so there's the centripetal force, or the centripetal inward force. You would have to split your FG vector. So I'll do it here. So if you think about the sphere, there's FG, but if you extend out that sort of axis, this theta right here that we're solving for, it's this theta here by vertical angles. So if this is that theta, you're going to see pretty clearly that the inward, right, if you think about the axis of the sphere, the dome, the inward force is going to be Fg cosine theta, right? So if you split up, there's that Fg, you get the cosine, Fg, I don't even call that inward, radial, whatever. Fg radial is just Fg cosine theta. Fg cosine theta minus Fn, right, because there's going to be that normal force before it flies off, is going to equal m and then v squared over r. So what's going to happen to understand this problem is that it's going to gain speed, right? It's going to gain speed, and it's going to gain speed. So if this side gets bigger, if the right hand side gets bigger, so does the left hand side. The Fg cosine theta is not changing. If anything, it's getting smaller, because as theta, if you think about your trigonometry, your unit circle, as theta approaches 90 degrees, its cosine theta approaches 0. So this is actually getting smaller. How do we make this whole thing get bigger? Well, Fn is going to have to decrease. Eventually, it reaches 0, and then after that point, it's going to just barely be in circular motion until this thing gains even more speed, and then we're not going to be in circular motion anymore. It flies off. But at that instant, at angle theta, Fg cosine theta equals mv squared over r. So mg cosine theta equals mv squared over r, and the m's dropped, so I can just actually erase this m. G cosine theta equals v squared over r. Cool. So we want to know, well, at what speed will this equation hold true, right? At what speed will the Fn equal 0? We got to go to conservation of energy. So for conservation of energy, the reason we're doing this is, I guess maybe there's a way he's dynamics or something. I don't know. Energy is the best way to go about this. It just is easy because we could say, well, the initial energy equals the final energy. So there's UG here, there's UG there. I'll just write that in actually. It'll be helpful. UG initial is going to equal, right, because it's not moving initially. It's all gravitationally, it's all gravitational potential energy. So UG initial is going to equal K, the kinetic energy linearly, translationally, plus K rotational, because it's going to have some rotational energy. It's a solid sphere, plus UG final. I'm either way going to be solving for like speed, which is in K, right? I'm going to have to subtract the UG final. What I can do is I can just do UG initial minus UG final. That would be the, it's not really change in UG, but it would be, because it's technically like negative change in UG. I'll just say change in U, right? So change in UG equals K translational, K rotational. So 1/2 mv squared plus 1/2 I omega squared. So what we can do now is just start substituting things in, or not substituting things in, let's make this mg. Mg, change in y, right? Change in height. It's because it's gonna, fall a certain amount of height, or distance, whatever. 1/2 mv squared plus 1/2 I omega squared. This I, right, rotational inertia of a solid sphere is 2/5 mr squared. Hopefully I don't know if you have to memorize that in AP Physics C. You might. Oh well. Times omega, right? Rotational velocity is just equal to v over r when we're dealing with rolling. So we can do v over r squared. What you're going to notice, I guess I'll just keep expanding things. So mg change in y. What you're going to notice really quickly is, first of all, the m's drop. So I can actually drop an m from each of these terms because everybody brought mass. That's a cool little reference. If you get that, you get $1 billion. 1/2 v squared plus 1/5 m drops, and then this is r squared times v squared over r squared. These are the same r, right? Like the rotational inertia r is the same as the rolling r, like the angular velocity r. So I can actually drop the r's. So now we get this weird looking equation. So g times change in y is equal to 1/2 v squared plus 1/5 v squared is 7/10 v squared, right? Because if you have 1/2, 1/5, the 1/2 becomes 5/10, the 1/5 becomes 2/10, you get 7/10, right? Yeah, you get 7/10. 7/10 v squared. So then we get 10/7 g times change in y equals v squared. Why am I solving for v squared? I could take the square root of this. I don't have to though, because I know I'm going to be plugging back in v squared. I need the square velocity anyways. Might as well leave it like this. So I can say g cosine theta is equal to v squared over r is 10/7 g change in y over r. So what I can do now is, hey, the g's actually dropped. That's kind of neat, right? So it doesn't matter what planet you're on. You can do this fun little bald man grape experiment. The change in y. Well, what's the change in y? That's kind of the tricky part here. So change in y, you got to use some geometry for this, or you can memorize, but that's kind of lame. So if this is the angle theta, right? So the grape started here and ended off there. If that's the angle theta, this is our radius r. This is also our radius r. We're looking for the difference in height. So if we were to draw like a horizontal line here, this line segment right here, that's what we're looking for, right? So we're looking for, let's just call it change in y. It's gonna be r minus this segment right here. So I'll call this segment x. It's going to be r minus x equals change in y. Hopefully you can kind of see that. Full length is y. I want to subtract x to get change in y because I'm left with change in y. What is x? Well, hey, because I made a horizontal with a vertical, this is a right angle. And if that's a right angle, and r is our hypotenuse, x is just r cosine theta. So I get r minus r cosine theta equals change in y. Let's plug that back in here. Cosine theta is going to equal 10/7 change in y, which is really just r minus r cosine theta over r. This is neat. The r's also drop out. So this dome could be like the dome in Las Vegas or something. It doesn't matter. The r's drop as well. So, yeah, that's neat. This could be any dome in the world. Cosine theta equals 10/7 r minus 10/7 cosine theta. Now I'm just solving for cosine theta. I'm just solving for, this should be 10/7, not 10, because it's 1 minus cosine theta at this point, 10/7. So what I do is, well, just to make this easier on myself, this is 7/7. So I'm gonna add this to both. I want to isolate my cosine theta really. So I get 10/7 cosine theta plus 7/7 cosine theta. That's 17 over 7 cosine theta, which is equal to 10/7. And then you would multiply this by 7 over 17, right? You're just saying the reciprocal. And I get, the 7 drop, I get cosine theta is going to equal 10 over 17. So it's just going to be whatever angle satisfies this, like, this ratio, right? Cosine theta is equal to 10 over 17. That's our answer. And hey, math, if you're a math teacher, they love things exact. So you would say theta, where am I going to put an answer? Well, where do I put an answer? Here, I'll put it here because the lighting here is better, I think. So theta equals cosine inverse 10 over 17th. They love things exact. I don't know why. Like, actually, I kind of understand. I don't know. I like math, but I love physics. So I'm just going to make this like an actual number so I know, like, oh, this is this many degrees. I'm in radians. Don't be in radians. That would be a fatal error. Go to degrees. So I can quit. Cosine inverse 10 over 17. I get 50, basically 54 degrees. So, but we'll be exact-ish for the math teachers out there. It's this many, 53.97 degrees. This is a cool result. This could be you could take a boulder, you could take a snowball. You don't even have to worry about the radius. You don't want to worry about anything. As long as they're roughly spherical, you're gonna see that after it's swept out, 53.97 degrees. That's when that thing is falling. You could place bets on your friends with this. You could be like, I got this ball, man. I got this grape. At what angle do you think it's gonna fall off? And they'll be like, oh, I think 30, because that's a special angle. I think 45. And you're gonna pull out your calculator. You're gonna get 53.97 degrees. Put some money on it, and you'll probably be pretty close, because you're not gonna get perfect spheres. But this is a pretty cool result. Though none of the variables matter. It's always gonna be 53.97 degrees for a bald man and grape problem. Thank you for watching. Hopefully this was kind of not that interesting, or kind of interesting. I don't know.